Hello, today we are going to continue with force and motion part 3. Right here, you're probably familiar with force equals mass times acceleration. What do you think that means? Type your answer right here. I just gave it to you. What would be the formula if you wanted to solve for acceleration? You can look back on your notes. You'll put that there. Use the formula to make your calculations. So right here, you're going to be looking for, it says a soccer ball was kicked. It had the mass of 42 kilograms and accelerated at 25 ms, meaning miles per hour squared. What was the force? So you're going to use your F equals m times a formula to get that answer. So your mass, which is 0.42 times 25, equals your force, and you will type your problem and your solution here. Same for this. A force of 20 newtons acts upon 5 kilogram block. Calculate the acceleration of the object. So you will use your mass and your force to equal acceleration. So A equals m divided by f. An object with a mass of 300 kilograms is observed to accelerate at the rate of 4 meters squared. Calculate. So once again, your acceleration, A equals m times divided by f. Type your solution and your problem down here and show your work. Now on our second slide, you're going to tell me use what you've learned about Newton's third law to explain what's happening in each of these situations. Type your responses in each of these speech bubbles. Explain in your own words how a rocket is able to lift off. So tell me, based on what you learn about the third law right here, and then explain in your own words what would happen if you were to let an untied balloon go. Why would it act this way? You're going to put your answer here. Explain in your own words what would happen if you were standing on a skateboard and then pushed the wall. Type your answer here. This is all based on the third law. Newton's third law is the law of action and reaction, meaning for every action there's an equal and or opposite reaction. Right here, you're going to look at the examples of Newton's laws and decide which law is best demonstrated in the example. You will click on and drag the numbers and the number icons to identify that law. So you'll take and you will move the laws to these particular things. Okay? And then on this fourth one, it says use the space to jot down notes, drawings that will help you remember important ideas from this lesson. Listen to the video and make a race summary. Let me fix that. Summary. Okay, so we're going to listen to this video right here together.
Grammarly is a digital writing assistant that you can download for free by going to Grammarly.com and clicking through the Add to
Clarendon Learning explores simple machines for kids. Hey kids, in the beginning, everything had a beginning. Think about it. Huge, bustling cities started out as little towns with little buildings. We wouldn't have supercars if Carl Benz hadn't built his first motor wagon. And we never would have gone to the moon if someone hadn't invented the wheel. The wheel and axle is an example of a simple machine. And this is what we're going to explore today. Simple machines. Let me introduce you to some important helpers of mine. We call them simple machines. The inclined plane, the lever, the wedge, the screw, the wheel and axle, and the pulley. These tools have made the work I do so much easier. I'd like to show them to you, and I'd like you to use your imagination. Are you ready to learn about simple machines? Awesome! Let's go! Keep in mind that a simple machine has few moving parts and should enable you to do more work with less effort and energy. Look at this person hoist a sail with a simple machine. She's doing more work with less effort. She's crossing the ocean with a simple machine. This is the inclined plane or ramp. It can be used to lift heavy objects from a lower level to a higher level. How much do you think this dump truck weighs? It weighs around 628 tons. That's 1,256,000 pounds. Whoa! And this inclined plane is helping this machine get from a lower level to a higher level with the greatest of ease. Using a gradual ramp enables you to travel up and down much easier. And using a ramp is the way that a person in a wheelchair can get up over a curb or into many buildings with multi-levels. Maybe the ancient pyramids of Giza were built using the inclined plane. I wonder what other simple machine might make good use of the inclined plane. Hey, how about the wheel and axle? Yeah, moving equipment up and down a ramp using wheels is easy. The wheel and axle are used all over the world for all sorts of things. Here's an example of my friend, Mr. Pottery Man. I wonder what he's making. I bet it's a cereal bowl to hold a lot of cereal. And what's he using to make that cereal bowl? You're right, a wheel and axle. Good job. The wheel is probably the greatest simple machine of all time. Think of everything the wheel can do and what we use it for. Just about everything in the world moves because of the wheel. Planes, trains, automobiles, bicycles, unicycles, wagons, horse carts, pickup trucks, hand trucks, wheelbarrows, skates and scooters. Wait, whoa, back up. Is that a 6-wheeled truck? Whoa! The wheel and axle have made the work we do easier and recreation more fun. I mean, how fun would a bike be with square wheels? Next, if you give me a fulcrum or a pivot and a plane, I'll give you a lever. Actually, 3 types of levers, depending where you put the pivot. Some examples of the lever as a simple machine are scissors, pliers, a baseball bat. Your arm and elbow is a good example of the lever. The lever gives us leverage to move things. A teeter-totter is a super fun, simple machine. Just ask Lily and Max.
Hello, friends.
The shovel is a combination of 2 simple machines, the lever and the wedge. Yes, the wedge is a simple machine and very powerful. With the wedge, I can split wood. With a knife as a wedge, I can cut through steaks and chicken and vegetables with ease. I like the wedge. I can use it as a doorstop and keep my door open. A nail is another example of the wedge, a very small but important simple machine. Look at the screw, a simple machine all by itself. With the screw, I can attach things to a wall. I can drill a hole. I can seal a bottle with a screw-on cap. And the spiral staircase? Yep, a screw. What about curly fries? I don't think they're a simple machine, but these sure do look yummy, and I'm getting hungry. But the screw is a very cool simple machine. Which brings us to the final simple machine. Last of all, but not the least of all, the pulley. The pulley is like a wheel but with a groove. With a couple of pulleys and a rope, you can exhibit superhuman strength. Look at this example of Mr. Kitty getting pulled up by a pulley. Look how huge that crane is. A lot of huge buildings all over the world are built by cranes. A simple machine. The elevator uses the simple machine technology of the pulley. And who loves elevator rides? I do. We just learned about the 6 simple machines. Do you remember what they are? The inclined plane, the wheel and axle, the lever, the screw, the wedge, and the pulley. Great job! These are the simple machines. They're around us every day. And when you assemble several simple machines together, you get cool things like cars, airplanes, and roller coasters. The bicycle uses many simple machines. Can you figure out what they are? Can you see the wheel, the lever, and the pulley? Good job! Today's assignment is to look around and identify the simple machines in the world around you. And while you're at it, check out the Clarendon Learning activity pages made for your grade level. Thanks for following Clarendon Learning. Be sure to subscribe. If you're looking for more teaching resources, check us out at clarendonlearning.org.
All right, so that is simple machines. And now that we have our simple machines, we're going to continue to talk about our other information that we have here. Okay, you're going to do a race format summary for that. And then on slide 5, we're going to review. I want you to rotate the 3 inner wheels to line up the correct description, diagram, and examples to the different types of levers. To rotate, you'll click on the wheel and then click and drag the rotate tool. Okay, so you'll take and you'll do this, and you will take it and rotate it by taking and moving it. Oop, see if I can get that properly done here. You're going to click on it and you're going to hit the rotate tool here. Okay, so this is your rotate tool. If I can get it to rotate properly. So here's your rotate tool, and you'll just take it and rotate it until you have the right answer. See how I rotated it? That's what you're going to do. Okay? Now, slide 6, I want you to take out a sheet of paper and fold one corner to the edge of an opposite side. Crease along the fold and cut off the triangle that you just made. Use a marker or a pencil or a pen and draw a line along the longest edge of the triangle. Lay your pencil along the shortest side of the triangle and roll the paper around the pencil, the marker, or the pen. So, what you should get is this right here. It should look just like this. Now, the question that you have to answer is, how does a screw make work easier? So a screw makes work easier because list your reasoning right here. Now, on slide 7, you're going to complete the table by clicking and dragging the cards to their correct positions. So you're going to tell me what is a lever, pulley, and wedge. And it's going to be one of these: a screw, wheel, and axle, or an inclined plane. Okay? And then where it says green place diagram here, you're going to take one of these picture examples and put them under a lever, a pulley, or a wedge. And then right here it says place description here. You're going to take these yellow ones and you're going to put the description of your lever, pulley, or wedge under it for each spot. Then you're going to take this last row and you're going to write the description. You're going to put the proper description in its place right here, here, and here that describes these particular simple machines. What is the purpose of simple machines? Compare and contrast 2 different simple machines. Listen to the video and write a summary in race format. So we're going to listen to this particular video here.
What can you do with your Prodigy membership? You can rescue and evolve all.
In this video, we're going to talk about efficiency and simple machines. Efficiency is pretty important when it comes to machines. The better the machine, the more efficient it's going to be. And so a machine that's not very efficient isn't a very useful machine. So what are we going to learn in this video? First, we'll learn different types of machines. Then we'll learn about the equation to calculate efficiency. Finally, we'll solve a couple problems to see how this equation works. When I think of a machine, I'm quick to think about a very complex machine that can carry out very challenging tasks, like a bulldozer that can push earth around like I would never be able to do with my hands and feet. But machines don't have to be complex. A machine is simply a device that can change force or increase the amount of motion from force. To keep things simple, we're going to discuss simple machines. There are 6 of them, and these are all machines that are going to work on an object in just one movement of the machine. The simple machines are the lever, the pulley, the screw, the wheel and axle, the wedge, and the inclined plane. We could also combine a bunch of these together to make compound machines like the bulldozer and do even greater tasks. But again, we're going to keep things simple in this video. We're going to focus on the inclined plane as we discuss efficiency. Now we're going to keep our discussion pretty introductory, and you can check out a more complex discussion in another video. Efficiency is a comparison of the work that a machine is able to do on an object compared to the amount of work that we use to operate the machine. We call the work that the machine does the output work, and the work that we use to operate the machine is called the input work. So an inclined plane makes moving an object to an increased height easier because you have to do less force on the object to get it to that higher position. So what does this look like? Well, let's look at a situation here where we want to move an object up on top of this bookshelf. Now let's say that the height of this bookshelf is 2 meters, and we want to lift our object up and put it on top of the bookshelf, lift it all the way up by 2 meters. Now suppose to do this, it required 24 newtons of force in order to lift the object up there. That means the work required was 48 joules. We were able to calculate that using our work equation here, which is work equals force times distance. And so we take the force, again, if it took 24 newtons to lift this book, and we raised it up by 2 meters, when we multiply those together, we end up with 48 joules of work. Now let's say that you were not strong enough to apply 24 newtons. No matter what you could do, you could not apply that force, and so you couldn't lift that book. This is where our machine comes in. So now we bring in our inclined plane, and we can push the book along the inclined plane and get it all the way up here to the top of the bookshelf. Now, let's say instead of 24 newtons of force, you only needed to apply 6 newtons of force in order to get that object moving. And you're strong enough to do this, so you can push the object all the way up on top of the shelf. Notice, however, that you had to move a further distance to go all the way up and put it on that shelf. Instead of 2 meters, let's say that the length of this inclined plane was actually 10 meters. And so that means you had to apply your 6 newtons of force over 10 meters, which means the work is going to be different. And so because you applied 6 newtons of force for a distance of 10 meters, multiply those together and you end up with 60 joules of work. Now we can compare these two together and we can calculate the efficiency. Now the output work is the work that the machine was able to do. And when we determine this, we just look at the before situation and the after situation. That's what we calculated right here. The book started here on the ground. That was where it was before. It doesn't really matter the path that it took. We just look at where did it end up. So if it started here and it ended up here, we've already calculated the work for the machine's output. So this is the output work. Now the input work is what we did, and so that's what we calculated down here. Let's go ahead and plug those into our equation. And so we have our output work divided by our input work, which is 48 divided by 60. And when we do that calculation, we end up with 0.8. Now, if we multiply that by 100, we'll turn that into a percentage. And so this inclined plane is 80% efficient. Let's look at a couple of other problems so you can have a little more practice. Here's a question that asks us to determine the efficiency of a machine that does 900 joules of work when the input force is 2,000. And so this number right here, that 900 joules, would be the output work. And so we can write down our equation and then plug in these numbers. And so here's our equation, output over input, and we can plug in 900 joules and divide that by 2,000 joules, and we end up with an efficiency of 0.45. Again, we're going to multiply that by 100 because it's better to report our answers in terms of a percent than a decimal. And so this machine is 45% efficient. Let's look at one more. In this problem, we have a pulley system that's 64% efficient. And we want to calculate the output work if we apply 85 joules of input. So once again, let's start with our equation. In this case, we're going to be solving for the output work, and we're given the efficiency, and it's 64% efficient. When I write this into the equation, remember that's going to go here where that E is. I'm going to write it as the decimal form, just like we would get when we do the calculation. So it's 0.64. To convert a percent into a decimal, just divide that by 100. And I'm going to calculate the output force, and I know the input force, that's 85 joules. So if I multiply both sides of the equation by 85, I'll be able to determine the output force. And so I'd have 0.64 times 85 joules, and I would end up with an output force, or the force that the machine would be able to do, of 54.4 joules. And that is efficiency in simple machines. So we learned about the 6 different kinds of simple machines. We learned the equation to calculate efficiency, and we learned how to solve problems involving that equation. Support the science classroom by subscribing.
Okay, so that is the efficiency in simple machines. What I want you to do is take and write a summary in race format, comparing and contrasting two different machines. And on slide 9, once again, we have another race format. And what you will do here is you will learn about speed and acceleration. So we're going to watch this video, and you're going to write about speed and acceleration.
I upgraded my soap.
So this is what we used to use. We're not going to do.
Speed and acceleration are physics concepts that we encounter every day, and an understanding of these concepts is crucial to most areas of physics. We think of speed as something we have when moving, and this forms the basis of speed's definition. Speed can be defined as the rate of change of distance. What exactly does that mean? Well, it means that an object's speed is a measure of how long it takes in terms of time for it to travel a given distance. From this, we get the following equation. Speed equals distance divided by time. The standard units of distance is meters, and time is seconds. Because of this, speed is measured in distance per time. For example, meters per second, or kilometers per hour. Let's look at an example. A car traveled 100 kilometers in 2 hours. What was its speed? So 100 divided by 2 equals 50 kilometers per hour. Now you try. A sprinter runs 100 meters in 12.5 seconds. Pause the video while you work out her speed. Did you get 8 meters per second? And another one. A jet can travel at 350 meters per second. How far will it travel at this speed in 30 seconds? Pause and have a think. Well, it travels 350 meters in 1 second. So in 30 seconds, it will travel 30 times 350, which equals 10,500 meters. So how far will it travel in 3 minutes? Pause and have a think. Well, 3 minutes is 3 times 60, or 180 seconds. So the distance it will travel is 180 times 350, which equals 63,000 meters, or 63 kilometers. In the same way that speed is the rate of change of distance, acceleration is the rate of change of speed. This means that the acceleration of an object is a measure of how much its speed changes over a given period of time. To calculate acceleration, we use the following equation. Acceleration is equal to change in velocity divided by time. Let's try an example. The velocity of a bus increased from 0 to 18 meters per second in 6 seconds. Calculate its acceleration. So acceleration equals final velocity minus initial velocity over time. Another example. A hungry cheetah saw a gazelle and decided to chase it. The cheetah was walking at 5 meters per second and accelerated to 20 meters per second in 5 seconds. What was its acceleration? Pause the video while you work it out. The sign in front of an object's acceleration indicates whether the object's speed is increasing or decreasing. If an airplane's acceleration is negative 40 meters per second squared, its speed is decreasing. The gradient of a line on a speed time graph represents acceleration. If the gradient is positive or goes up, the object has a positive acceleration. If the gradient goes down, the object has a negative acceleration or deceleration. What's the acceleration of this object between points A and B? The change in speed is 25 minus 5, which equals 20. The change in time is 6 minus 2, which equals 4. So the acceleration is 20 meters per second over 4 seconds, which equals 5 meters per second. Is the acceleration large, small, or 0 in these time graphs? And is it positive or negative? Pause the video while you think. So that's how speed and acceleration are related and can be calculated.
If you like the video,
All right, so that is our speed and acceleration notes. You're going to do a race summary right here. And then on slide 10, what you're going to do here is you're going to tell me what is speed, what is acceleration, how can you calculate speed, and graph the acceleration looks like distance times graph. You're going to move these to the appropriate places here. And on slide 11, you are going to use what you've learned about Newton's third law and explain what is happening in these situations. You're going to type your responses in the text boxes here, and then you're going to match in these orange boxes, match which one goes to which. A change in speed or velocity over a specific amount of time equals time and distance or equals distance and time. A change in distance over a specific amount of time would be what? Time and distance or distance and time. On 12 here, you are going to solve these particular problems and tell me what kind of formula that you are going to be utilizing. Same for this one. Right here, you're going to take and tell me which one of these should be put into this box. 1, 2, 3, or 4, all the way across. And that is all for today's lesson.